All right, so if you're serious about a career in AI, there's some things you just have to know. And deep reinforcement learning, that's right at the top of the list. What we're going to do here is take a look back at some of the key ideas from Stanford's big Deep RL course, CS224R. We'll unpack the core framework that's behind some of the craziest AI systems out there today. So yeah, let's dive in. So, first question, why should you even care about Deep RL? Well, here's a pretty good answer. The course instructor actually asked a friend that same question, and this was the reply they got. Look, beyond all the cool science, let's be real. Mastering this stuff has some pretty significant career upside. We're talking about very real, very big numbers.
Okay, but it's not just about the money, obviously. The motivation goes so much deeper. I mean, we are talking about training actual physical humanoid robots to do things like dance. And they learned it all just through trial and error, which is just wild to think about.
And then you've got this. This is the tech behind DeepMind's AlphaGo, the AI that beat the world's best Go player. And it wasn't just about winning. There was this one moment, Move 37, that was so creative, so alien, that it just broke the minds of human experts. That's when we knew this wasn't just about mimicking humans. This was about discovery.
And look, it's not just fun and games or cool robots. These very same RL techniques are being used right now to design the actual physical chips, the hardware. We're talking about the things that power Google's TPUs. Think about that for a second. It's literally AI designing the brains for the next generation of AI.
Okay, so dancing robots, world champions, AI-designed chips. That's the hype, right? That's the what. But now, let's get into the why. Let's go beyond the headlines and look at the core ideas that make all of this stuff tick.
So what makes this different from, regular machine learning? The big, crucial idea is this. Deep RL is all about making a sequence of decisions, where every choice has a consequence down the line. It's not like supervised learning where you have a nice, neat answer key telling you, yep, that was the right move. Nope. Here, you have to learn a whole strategy from scratch, just through trial and error. And that's much closer to how real intelligence actually works.
And to really get this, you kind of have to shift your whole mindset from the typical way we think about ML. It's a whole new ballgame, learning without a label.
Okay, this table breaks it down perfectly. On the left, you've got supervised learning. You know the drill. You have a big data set with inputs and the correct labels, right? Cat picture, cat label. The goal is just to learn that mapping. But on the right, reinforcement learning is totally different. The input isn't a data set, it's experience. The data is sequential. What happens next totally depends on what you just did. And the feedback you get isn't a right answer. It's just a reward signal, a number. So you see, you're not learning a simple mapping anymore. You're learning a whole behavior.
All right, so to talk about all this properly, we need to get on the same page with the language. Let's run through the core vocabulary real quick.
First up is the state, which we just call S. You can think of the state as the God's eye view, a perfect, complete picture of everything that's going on. Like knowing the exact position of every single piece on a chessboard. But, in the real world, you rarely get that. More often, our agent gets an observation, or O, which is just a partial peek, like a single photo from a robot's camera.
Okay, next we have the action, A. Super simple. It's just what the agent does. It's the decision it makes. Could be moving a robot arm, typing the next word in a chat, or picking the next song on your playlist. It's the agent's output into the world.
So, how does it know what's a good action versus a bad one?
That's where the reward comes in, R. It's just a number, a simple little signal from the environment that says, good job or bad job. You get a +1 for winning, a -1 for losing. Maybe it's a thumbs up on a recommendation. That number, that is the only thing the agent is trying to make as big as possible.
So you put it all together, and what do you get? You get this loop, this rhythm. The agent sees the state, it takes an action, it gets a reward, and sees the next state. And then it does it again, and again, and again. This whole sequence, state, action, reward, new state, we call that a trajectory. And that is the raw data. That's what the agent actually learns from.
So now that we have the lingo down, the goal is actually super simple to state. The agent's entire purpose in life is to maximize the total reward it gets. But there's a problem, a big one. What if the world is random? Because, well, it is. The world isn't predictable. That other car on the road might do something totally unexpected. And sometimes the agent itself wants to be a little random, to try new things and explore.
And that leads to a really crucial point. Because of all that randomness, the agent can't possibly guarantee it'll get the best score every single time. It's just not possible. So instead, the goal changes. The goal is to learn a strategy. We call it a policy, that's the little pi symbol, that gets the highest score on average. It's all about maximizing the expected reward over thousands of tries. It's playing the odds to win in the long run. Okay, so if you've ever dipped your toes into RL, you'll notice something weird. There's like a whole zoo of different algorithms. It's not like supervised learning where everything is basically some flavor of gradient descent. So what gives? Why are there so many different ways to do this?
Well, it all comes down to one thing: trade-offs. There's no one-size-fits-all solution here. You can kind of think of it like this. Is it better to learn by doing or learn by thinking? For example, if you're in a video game simulation, data is basically free. You can play a million games, so you might use an algorithm that just learns from raw practice. But what if you have a real expensive robot? Crashing it is bad. Data is expensive and dangerous. In that case, you might want an algorithm that learns a little model of the world first, so it can think and plan before it ever moves. Each strategy has its pros and cons.
And this is where it gets really exciting, I think. This is the edge. For all the cool stuff we've seen, there are some massive, fundamental problems we still haven't cracked. This is the open frontier. I mean, how do you get an AI to take what it learned in one situation and apply it to something totally new? That's a huge one. Or how do you get it to solve a really long-term task, like, I don't know, cooking a whole meal from scratch, where the payoff, the tasty food, doesn't come for a long, long time? And maybe the biggest one of all, how do we get robots to just practice on their own, without a human constantly having to help them out?
And that really brings us to this final thought from the course, which I just love. There's this story about a researcher, Yivan, who was teaching a robot to hit a hockey puck. But after every single try, Yivan had to go and put the puck back in place himself. And eventually he realized, wait a minute, I'm doing more work than the robot is. So the real question, the multi-million-dollar question is, how do we fix that? How do we build AIs that can reset their own experiments and truly learn on their own? Whoever figures that out, well, that's going to be the next giant leap.